Hello everyone, thank you for coming to listen to this presentation. I'm Zhengqing from Tokyo Tech. I'm very happy to present our latest work, the OmniGlobeVR, a collaborative 360-degree communication system for VR. So there is a need for a collaboration or communication system that the designers and developers who are outside of VR can easily instruct or review the behavior of an occupant who is inside of VR for prototyping VR or 360-degree contents. There are several related work which can be used for this case. For example, shared VR systems require all users to wear HMD to view the VR space together. So the designers and occupant both have semi-immersive VR view. Well, it brings an issue. Since the designers wear HMD, it's not easy for them to access physical objects anymore. The Dollhouse VR allows designers not wear HMD. As you can see in the pictures, the designers can communicate with the occupant through a 2D flat display, and the designers observe VR space from a God view. So the limitation in this system is designers cannot get the same first-person view of the occupant. Therefore, the goal of the OmniGlobeVR is to address these two issues. And here is the OmniGlobeVR. Two benefits of these tools are that designers don't wear HMD, so they can easily access to both VR space and real space. The second is that it supports both first-person view and God view. Now I'm going to show a video to introduce the OmniGlobeVR system.
In this video, we propose OmniGlobeVR, an intuitive collaboration system enabling communication and cooperations between multiple remote workers in VR and non-VR environment. A VR user, known as the occupant, will be able to use the VR headset to view the virtual environment. In this case, we are using the HTC Vive headset. On another side, the VR space of the occupant will be shown on the OmniGlobe, a spherical display system. This allows multiple non-VR users, known as the designers, to cooperate between each other and also with the occupant. This can be achieved through the physical interaction with the OmniGlobe, verbal and non-verbally. The OmniGlobeVR uses a projector to display the VR space onto the surface of the spherical display. Furthermore, the system has a 360 camera mounted on the top for sharing live previews. Underneath was a platform that supports 360 rotation in case when the space is limited to walk around for different viewing angles. The system renders the VR space onto the spherical display with two view modes. The 360-degree first-person mode allows the occupant to share the 360 surroundings with the designers in the first-person perspective. However, due to the nature of the 360 view, it can be difficult for the designers to understand where the occupant is looking at. Therefore, we implement a view awareness cues to solve the issue. In general, the system tracks the head rotation of the occupant from the VR head-mounted display. Then, the rotation data is used for rendering as a red translucent frame shown in the spherical display. This allows the designers to see and understand the view direction of the occupant. In the third-person mode, the designers will be seeing the VR space from the top-down perspective. In another word, a third-person view from the occupant is shown on the spherical display, allowing the designers to see the VR space along with the spatial information of the occupant. However, this is cropped as an independent sector window that follows the designers as they rotate the display or moves around. Likewise, a similar red translucent frame is shown but from a distance to the 3D avatar. This allows the designers to not only understand where the occupant's virtual position, but also the view direction inside the VR space. Furthermore, a face window that shows the preview of the designer's face are rendered at the upper area of the VR space. This allows the occupant and the designers to communicate and work coherently even if it is inside or outside the VR space. At any time, a new designer could join the system and start working with the other collaborators. This creates a new face window utilized to the designer that can create awareness to the occupant. Apart from just showing the face of the designer, The face window could also be used to support gesture communication. The system tracks the physical position of the designers using the QR code attached on the chest in order to map it to the corresponding virtual position. This ensures the face window will be always shown at the viewed direction whenever they rotate the spherical display or physically walking around it. As visual feedback, the face window can also be seen on the OmniGlobe by the designer. To make use of it, a designer could combine with the hand gesture to give instructions to the occupant by pointing using the hand.
In the experiment, 6 pairs of the participants, 12 people in total, were recruited. The task requires 2 participants to cooperate, one being on the occupant side and the other on the designer side. In the VR scene, 24 objects are placed around the occupant. The designer will get an instruction note with some target objects information. So the task requires the designers to indicate the listed target objects to the VR occupant one by one, and the occupant will get an answer which is the correct target. We compare the OmniGlobeVR system among the 3 configurations. In the first condition, the system is configured in the first-person mode with the face window. In the second condition, the system is also configured in the first-person mode but with a white solid window. The only difference is that there is no live preview of the designer shown in the solid window. In the third condition, OmniGlobeVR system is configured in the third-person mode with the face window. The study was within group design, with each pairs of participants trying all three conditions. The order of the conditions as well as the test targets was counterbalanced between 6 groups of participants. For a group of participants A and B, they have to do the task at 6th round. The comparison was done between conditions based on the results. Comparing 1PFW conditions with the 1PSW can help us to understand the impact of the face window. And comparing the 1PFW with 3PFW can help us to find out the difference between first and third person mode. We find a significant difference between 1PFW with 3PSW condition, which is measured by the correct rate of the occupant's first answer. For the results of spatial presence, mental efforts, and system usabilities, the 1PFW condition has better result than 1PSW condition in both designer side and occupant side. And the 1PFW condition has better result than 3PFW conditions in designer side, while no difference was found in the occupant side. User preference results measured by post-experiment questionnaire also show that participants on both sides had a huge favor towards the 1PFW across all 3 aspects. And using 3PFW was also preferred for a minority of participants in the occupant side. Based on the results and the participant comments, it seems that the face window provided comparable user experience and system usabilities, with its benefits including stronger spatial presence and a better understanding of the partner's focus. Meanwhile, visual feedback of the face window makes the participants on the designer side have better confidence at giving the instruction and also ensure their instructions are delivered to the VR user accordingly. As for the difference between first person and third person mode, the results show that the first-person view mode is more preferred by the participants. The third-person view mode allows the participant to see more things, which helps for quick searching. However, the third-person mode suffers from the visibility issue caused by resolution. So due to the time limitation, please allow me to end my talk here. Thank you very much for your attention.